We'll start off today's lesson on half-life, and then we're going to get into fission and fusion, and then we'll have some practice problems that we're going to work through. And the first thing just to mention when it comes down to half-life is the amount, the time it takes for half of the material, the radioactive material, to decay. And just a reminder, with decay, it's going to become something else. It's going to become another element when you have the decaying going on. And not all material, radioactive material is the same. You've heard of carbon-14. It's carbon dating. When you hear of carbon dating, the thing with carbon dating has a half-life of about 5,730 years. So you can kind of take a look and you can figure out how long something has been dead for. It has to be something that was once living. Something has been dead for that would have a carbon, made of carbon. And if you remember from biology, carbon is the molecule of life. It makes it's the backbone of all of our different macromolecules. Not going to teach you that lesson. I taught a couple of years ago that lesson. But it's the backbone of all these molecules, these macromolecules that make up life. And when you're living, you got to eat. And when you eat, you're going to keep on eating things that are living, and you're going to maintain your carbon in your body. Some of it, a fraction of it, is radioactive, carbon-14. It's going to decay over time. While you're living, you eat. You keep on supplementing. You keep on adding the carbon-14 to your body. But after something dies, it no longer eats. And when it stops eating, that carbon starts to degrade, and it will keep on decaying, and then you can track how long something is not living anymore. And so that's often been used. Some of these with iodine may not be. First of all, for living organisms have carbon. You can find iodine and things like that in living organisms, but with a half-life of 17 million years, that's how long it takes for half of the radioactive material to decay. It's not very, it doesn't decay very fast. It might not be as useful, but it might be useful for something else. So that's just a little bit more about carbon-14 and rate. And it's called radiometric dating. So if you ever heard that term, it's just using the half-lives, figuring out how much radioactive sample remains. So this is what's happening as something decays. One half-life, half of the sample. For radium-226, half of the sample will remain after one half-life, or 1,600 years. You go another half-life, you're going to have a quarter of the sample. Go another half-life, you're going to have an eighth of the sample. Therefore, so on and so forth. And there's going to be an equation you're going to see that will relate to that we'll use. Sometimes, so for this unit, sometimes it's going to be easy to just do a quick equation. Sometimes it's going to just be easier to go through and just make a table. And when you make a table, you just think, okay, well, how many half-lives? You can make a table two ways. But you're going to think of how many half-lives. You're going to start off with the original amount or original percent, and you're going to say one half-life. We're going to divide that by 2, and you're going to put that in here. You're going to take, okay, one more half-life. You take that number, divide it by 2, put that in here. And you can just kind of walk through and figure out how much sample. You can figure out how much percent is left. You can figure out how many kilograms is left. Or you can figure out the fraction remains if you're doing that to 1 rather than 100%. And then if you're looking for the non-radioactive sample size, the one that the decayed amount, you would just take the original sample size and subtract whatever decayed, and that would leave you with the non-radioactive amount. So once one half is decayed, one half is non-radioactive and one half is still radioactive. When 1/4 is left that's radioactive, well, 3/4 is going to be what would be non-radioactive. So you can just kind of follow through there. Here's our equations that you're going to use today. If you want fraction left, that's y. It's going to be 1 over 2 times little n is number of half-lives. If you see this t over 1/2, that is going to be the time of one half-life. And all you'd have to do is take the total time and divide it by the number of half-lives that occurred. And so here's our first equation, first problem. How much of the original radioactive material remains after 4 half-lives? So I want to see you going up. So how much of the sample remains? We can go with fraction. If it doesn't say otherwise, you can go with fraction after n of 4 or 4 half-lives. Go ahead and take your equation. Y equals 1 over 2 to the n. And then the work there would be 1 over 2 to the 4th. Get that answer, figure out what your answer is. And when you got your answer, it should be 1/16 or 0.0625. Tomorrow we have an E-class quiz over this. Put that 0.0625 if that was the answer. Don't put 1 over 16. I don't know if E-class would give you credit for that or not. So do the decimal amount. Any questions there? You good? Okay, this one is just kind of a follow-on question because this one actually gave you how many grams of the sample you had in the first place. So if we know from the last time, after 4 half-lives, you have 0.0625, that amount remains. All you have to do is take that number and multiply it by the 56. Go ahead and do that and figure out how much sample size, how many grams of sample would remain after that, the 4 half-lives. Think you got it? And you should have 3.5 grams. Okay, and then I just want to show you a table. If I was trying to figure this out using a table, all I would do is after 0 half-lives, I'd put the 56 grams in, and I'd just go 1, I'd cut it in half, 2, cut it in half, and keep on going every single time. And if I was asked for radioactive fraction, I would have got to that. I would just put the 1 over 16 in the calculator, got the decimal. So that's how you do it with a table. How long is a half-life for a substance that has 2.5 half-lives every 50,000 years? So the number of half-lives for N is 2.5, and the time is 50,000. How long is the half-life? And if you get your answer, you should see 20,000 years. Any questions on that one? Okay, next example. D, here it says 100 gram of unknown reactive material has a half-life of 4,000 years. How much will remain after 20,000 years? So let's go ahead and take this information. Let's figure out how many half-lives occur in the first place. And then we're going to use that in the second part. So use that information, rearrange it, figure out how many half-lives there are. And when you figure that out, you should find that it's 5. And so now that we know there's 5 half-lives, we can go ahead and take it a step further. We can either go to the table if you wanted to, or we can go ahead and figure out the fraction. And so I'm going to go ahead and figure out the fraction first. Once again, table worked fine. I'm not grading you on that you're doing the math, how you're getting the answer. It's just that you are getting the answer. And so when we figure out and do the work, we're going to have 1 over 2 to the 5th. That's going to tell us the fraction left. And when you get that answer, you should have 0.03125. And then just take that number And you're going to multiply that number by the original sample size, and that's going to give you the grams of sample left. And use whatever unit. If they told you kilograms, you'd use kilograms in your answer. Tell you grams, use grams in your answer. And so since it's just multiplied by 100, there's going to be 3.125 grams left. Any questions on that one? So make sure I see, I'm looking for you working. Make sure you're working, not getting distracted by your cell phones. Most of you guys are. Nick, you didn't work? I'm just going to go through the first one for now, and so that way you can check if you got stuck anywhere. That one's pretty simple, except you're going to take that fraction left and you're just going to multiply it by 100 to get a percent from a fraction. So you get 0.098%. I think on the quiz tomorrow I only ask you for fractions, so you're not going to have to do the percent, but if, well, maybe I don't. Now that I think about it, I might have, but you could always go and take 100%, cut it in half, cut it in half, cut it in half, cut it in half, keep on cutting in half. It's good to use a table so you don't lose track of how many times you cut it in half. And that gets you to the same answer. Okay, substance that starts off with 400 grams, how much will remain after 5 half-lives? So you could figure out fraction left, and then you could just go ahead and multiply it by the 400, or you can do the table, which would result like that. So the other option would have been y equals 1 over 2 to the n, which would be 5. Once you do that, you just multiply that value times the 400 grams, and that would get you to that answer. Okay, for this one, if I give you any problems like this, I will stop at a whole half-life, because you could go off how many complete half-lives occurred after the 12.5 of the original sample remains, 12.5%. So you could say, oh, well, that's 1 point. You could say y equals 0.125. And then you can say, well, okay, how many complete half-lives n equals question mark, but then you're going to be left off doing this 1 over 2 to the nth power, solving for that. And so I'm not going to worry about the math on that right now, but you could have done it that way if you feel comfortable with the math, or you could just go ahead and start cutting in half, cutting in half, cutting in half. So you would have started here, okay, 100% at 0, 50% at 1, 25% at 2, 12.5% at 3. That is what you're asked for. Actually, that's what you're asked for, and that's 3 half-lives. So if I give you a problem like that, the only way to get a decimal, like a partial n value for the number of half-lives would be if you did do the equation I showed you. I'm not going to do that. I'll give you, if I have a question like this, it's going to be a full half-life. So it might be 5 or 2 or whatever. But for this question, it would have been 3 as your answer. Any questions there? We good? Ready for the last one? Which one? Number 2 was 12.5 kilograms. So if you did it the fraction way, you would have done 1 over 2 to the 5th, and then you would have multiplied it by the 400. But if you're doing it this way, you just cut the 400 in half, adding a value every single time, cut it in half, cut that 200 in half, cut that 100 in half, cut that 50 in half, cut that 25 in half, and now we're at 5 half-lives. So that would be the table way to do it. And it's always good to do, if you're doing the table weight, especially if it's like 5 half-lives, then make sure that you do it on do it on paper. So you don't want to lose track of how many half-lives you went through. Also, another thing that's really easy to do to make a mistake on, don't start at 1 half-life. If you start at 1 half-life, you would have done too few half-lives. So make sure you have 0 for the full sample and then go from there. Okay, how many complete half-lives have occurred if 18.5 grams of an original 600-gram radioactive substance remains? The way I went about this was just taking the 600, dividing it by 2, doing the table over and over and over. And so after cutting in half, cutting in half, cutting in half, cutting in half, I finally get to the 18.75 grams, and I find that was after 5 half-lives of that occurred. Once again, making sure you start at 0 in the full sample, not 1 in the full sample. 1 would have got you the wrong answer. And then just cut it in half from there. Any questions on this? Okay, so I had the PowerPoint on there. If for some reason I was going too quick for you, the PowerPoint you'll find on my website on the e-class. And let's go ahead and finish off the last few little bits. So this is the last that we're going to cover right now for my physics class with you. And we're going to go pretty simple. So I'm just going to tell you a few facts that I need you to know. First of all, nuclear fission. Next to fission, somewhere over here, write down splitting. I think I have it in here, or at least highlight it. That's going to be important. We're going to have a large atom, like uranium, and we're going to split it. And what you see in this animation is what occurs. You have a neutron coming in, hitting that large uranium. It's going to break up, and when it breaks up, it's going to emit 2 more neutrons. Well, those 2 neutrons, there was 1, now there's 2. It's going to keep on going out, and it's going to break up more and more of that uranium. And you have a new nuclear reaction going on as long as you have enough substance. Also, when coming up with how much energy you have, a little bit of that mass is just going to be converted into energy. And that would be from Albert Einstein's E equals mc squared equation. You can figure it out. So for this spontaneous reaction, and spontaneous means something that's just going to occur. For this spontaneous reaction to occur, you need enough of that uranium in the first place. If you don't have enough uranium, there's not going to be anything to split. You're not going to have that energy produced. And what I need you to do is highlight this, because I'll ask you a question tomorrow on tomorrow's quiz. It's what we use currently. It's the way the reactions are done in a current nuclear reaction for energy. So if it was a nuclear sub or nuclear power plant, they're producing energy doing this. And that's one of the things I just need you to know. Current technology allows us to use nuclear fission, that splitting of a uranium or some other large radioactive material element. And so we can harness that energy that comes from that mass. Nuclear fusion. Go ahead and fusion. Right now next to it, just put down putting together. Putting together, because fusion's putting together. If you fuse something, you put it together. And in this case, we're fusing 2 hydrogen atoms. And when these 2 hydrogen atoms come together, they form a helium. And that neutron's given off in the process. And this just kind of reminds me, I want to talk a little bit more about fission. So I'll just go back to the slide for a second. Fission, there's problems with nuclear reactions using nuclear energy the way that we do it right now. It produces a lot of energy. That's a good thing. But the problem is the waste that results from the reaction is still radioactive, still dangerous. And so all we know right now, and it has large half-lives. So it takes a long time to decay. So you have this dangerous stuff that takes a long time to decay. And what we do, for the most part, is we find a hole and we dig it in that hole. We find people who aren't living in the area, and we go dig it in whatever mountain or whatever place. And there's problems that occur. If you heard of Fukushima a few years back, you had a tsunami, damage to the power plant. Often with energy, it's important to have water close by. And so we had the water close by, but a tsunami came in, destroyed some of the power plant, and the result is some of the waste was leaking. Nuclear waste was leaking into the water. You have stored in Washington, gallons a year are being trickling out of this power plant in Washington. That's damaging, that's dangerous. Most likely someone doesn't live right next door, but probably someone lives close enough to be affected by that. Nature is going to be affected by that. When you had a nuclear reactor meltdown in 3 Mile Island, Pennsylvania, have you heard about that? There's like massive leaves and just weird things that were occurring. Frogs with, I don't know, 2 heads. But there was a lot of stuff going on there. That doesn't mean it's going to always happen, but enough radioactive material creates extra mutations. You're going to have some changes that go on with life. So that's a problem. When it comes to fusion, you have helium. Has anybody ever used helium before? Get a helium balloon, what does that do? Makes your voice really high, right? And so it's not the kind of danger that we have with nuclear fission the way that we use it today. But when you think about what's going on here, this produces 10 times more energy. That's a good thing, right? It's a good thing, except energy usually comes with heat and a lot of other things. So it produces all that energy, and this is the energy of the stars. Maybe write that down somewhere. When you think of nuclear fusion, stars are harnessing its energy. You don't have anything living in the sun, so nothing's going to be destroyed by that energy. Well, in order to produce this energy, this 10 times more energy than fission, we don't have a current container that can contain it. So we can actually do fusion and we can produce 10 times more energy, but then it destroys whatever we made it in. So it's not cost effective. And that's where Lockheed Martin said they were there. They had something going on. If someone takes this fusion, I mean, that's even better than solar. Solar energy takes energy from the sun. Well, fusion is the sun. So you have that energy that can be harnessed, and that's going to be the energy of the future, right there. Maybe part of the mix, but it's not currently done. So Lockheed Martin, if you want to research that, as of 2020, research was still ongoing. The reason why I said 2020 is because I'm throwing this lesson on YouTube, and so it might be 2030 someday, and they might already have this. But in 2020, it wasn't possible. Well, no, it was possible. It just wasn't being used because it wasn't cost effective. It wasn't cost effective. So let me just do a quick review of alpha, beta, and gamma decay, because you're going to look at the next reactions. I think there's like 9 or 10 reactions in a problem set, and you have to determine what's going on. If you see something big like a uranium being broken down, and you don't see an alpha or beta particle in the reaction and the results and the products, then the answer is probably going to be nuclear fission. If you see a helium, but be careful. You see a helium and you see a neutron, not just an alpha particle, because it didn't break down, it formed. So the key there, the difference between nuclear fusion is that you have this thing that would be considered an alpha particle, but it's not, because it didn't break down from a larger element giving it off. These were actually put together to form that helium. So watch out for that. And then lastly, if you see a helium as a result and it was a product from a single reactant, then that's going to be alpha decay. If you see that beta particle coming from a single reactant, and that another, the result of that beta decay is that you have an extra proton created from a neutron, then that's going to be beta decay. And then if you just see the same thing both places, but a little energy or a photon symbol or a gamma ray symbol, then that's going to be the answer that you'll be looking for gamma decay. So go through the problem set. And if you're at home, you can go ahead and do the problem set. Maybe you want to scan this. Don't look at the answers until you try to come up with it yourself. But at the bottom of the page you see right here, that's going to be the stickman physics page with the same questions. So at the very